gain here, fire. So it's fine, but we have a minimum gain of 1. We cannot go below a gain of 1 in this configuration because of this 1 term here. Just something to think about compared to the future configurations we're going to go through. This next configuration is called the buffer, or what is sometimes called the voltage follower. The buffer is really just a non-inverting amplifier without a feedback resistor network. And so that's realized as just shorting the output directly to the inverting input. Now this configuration, in order to keep the inputs the same, V minus equal V plus according to our voltage rule, the op-amp must produce a voltage VO, which is exactly equal to VS. Because if V plus is equal to VS, and V minus has to also equal VS, and the only way that happens is the op-amp produces an output VO, which equals VS, which is set back to that inverting input. So that's to say that its gain is 1. Now, that doesn't make any sense because if I wanted to amplify the signal, make it bigger, what's the point? So it makes sense of why we would ever want this in the real world. Let's get back to the first video in the series and perhaps our existing circuit analysis knowledge. Now let's think about the loaded voltage divider. That is a voltage divider with a load that has across its output. So in this case, when we attach a load RL across the output of the divider, we actually change the very voltage at the output because the load draws current from the divider and alters the entire voltage divider equation. Can you think of a circuit which will not alter the output voltage of the divider, yet can still drive the load RL? And here's a really, really big hint for you. The input resistance of a buffer flash device is practically infinite, and the output resistance is ideally 0. So here's a solution I was really trying to hint at. Basically what we've done here is we've detached the load resistor RL from the voltage divider, and in between we've inserted an op-amp buffer. So how does this help us? Well, the golden rules tell us that the inputs of an op-amp draw no current. So if you attach the output of a voltage divider to the input of an op-amp, no current flows out of the output of the divider. And this means, as we know, that we don't draw any current from the divider, as the voltage at the output of the divider does not deviate from the voltage we expect using the voltage divider equation. Thus, the output voltage of the divider will not change when an op-amp buffer is attached. Basically, what's happening here is the op-amp is observing the input voltage, which is in this case the output of the divider, and replicating that voltage on its output. So it's really taking a copy of the input and pasting it on the output. And now, we'll think about an ideal op-amp that has ideally 0 output resistance, so that means that it can supply any amount of current to the load. And the voltage divider circuit and the load are isolated from each other. They don't use the same electrons, if you will, because the op-amp in the middle is acting as a middleman, playing telephone, the input and the output, hence the name buffer is used. Next up is the inverting amplifier, and it looks like this diagram over here on the right. With the inverting amplifier, we now connect the input to the inverting terminal, and you'll notice that the non-inverting terminal is connected to ground. So again, we're asked, what is the closed loop gain, VO or VS, for this configuration? So if V minus has equal V plus by our golden rule, then V minus equals at the inverting input has to sit at 0 volts because V plus has to be ground, and we know that ground is 0 volts. Also, recall that the inputs are not yet drawing current, so no current should have for the non-inverting terminal. Now, what's called the node which connects RI and the inverting input, what's called that node 1. And now we'll perform the Kirchhoff's current law or KCL analysis at that node. I'll assume that the current associated with these two resistors, that is RI and RF, are flowing into the node, and that current IN is flowing out of the node. And that might raise a flag your head IN, because you know that no current flow into an op-amp. And you're right, but we're going to see that there for a given output signal. So our KCL equation is going to be II plus IF minus IN, all equals 0. Now, we want these currents in terms of voltages and resistances, because we want to find the closed loop voltage gain, VO over VS. So how can we define the current through, say, RI? Well, we know that the current through resistors, just the difference in voltage across it divided by its resistance. So the difference in voltage across RI, well, it's going to be VS minus 0. Here's V minus sitting at 0 over RI. So the stage is just going to be VS over RI. And that's the first term of our nodal analysis, which we have nodal analysis where we have voltage and resistances. So that's the first term, that's VS over RI. And so now how you define the current through RF? Well, you're going to see it on the screen, but it's going to be at the top of the resistor, which is VO minus voltage at the bottom, which is 0 over resistance, which is RF. Here, VO over RF. And so the current IN, which points into the op-amp inverting terminal, well, how should we put that there? Because we know that no current flows into an op-amp. So that's 0, and that goes away. So you set that all equals 0, and we get a final nodal analysis equation here. And now it's just a matter of rearranging to solve for the closed loop gain, which is actually going to be minus RF over RI, and that is the gain for an inverting amplifier. Now, interestingly, in this configuration, we see that the voltage on the output is inverted. Let's say that if we were to apply a positive voltage to the input, that is if VS was positive, then we would get a negative voltage on the output. That would mean that VO is negative relative to ground. Also, whereas in the non-inverting amplifier that we looked at a couple slides ago, we noticed that we could not amplify by a value less than 1. The inverting amplifier can. That means that the inverting amplifier actually has the ability to be an attenuator, which is something that reduces signal strength, in addition to being an amplifier, which is something that decreases signal strength. And one final thing to note is that the input resistance of an inverting amplifier is effectively the value of the resistor RI. Now, the internal resistance of the op-amp is still infinite, as we said, but in this configuration, your source, so in this case that's DS, your source sees the value of the resistor RI as the input resistance of the amplifier. So I just mentioned that because it's a common trap for young players, because if you use too low a value keep that in mind. Next up is the summing amplifier, and at heart the summing amplifier is just an inverting amplifier configured to produce the sum of its input voltages. So I say it's just an inverting amplifier at heart because if you look at the diagram, the right half of the diagram is identical to the standard inverting configuration, and the left side of the diagram is actually really similar too. We just added on 2 more inputs. So you know what it does? It finds the sum of the input voltages. So how do we get to that conclusion? Well, we're going to start off by doing HCL analysis on this node right here, on the inverting input, just as we did before. And of course there's going to be 5 associated currents with this node, and they are I1, I2, and I3. Those are the input currents. The feedback current, IF, and the op-amp input current, IN. We know IN doesn't really exist, but we're just going to use it for now. As far as the HCL equation we're going, well, it's going to be I1 plus I2 plus I3 plus IF minus IN equals 0. And the HCL correlated measure means the way these HCL equations, if the current is entering the node, it is a constant current, and the current is leaving the node, it is a negative current. So this is like the interesting thing is the input output voltages of the current. So we find the voltage current relationship for these currents. So how do we do that? Let's look at current I1 is close to the resistor. Well, how do you find the current through the resistor? Let's see the voltage across that resistor. Its resistance. So the voltage across I1 is going to be V1 minus 0, because this is a node sitting at 0 volts because the non-inverting input is attached to the ground. So that's going to be V1 over R1. And that's the first term in our nodal analysis equation here, V1 over R1. And so the same thing follows for the next few inputs. For R, for the current I2 we passes through R2 is going to be V2 minus 0 over R2. That's just going to be V2 over R2. And for the third, current I3 is going to be V3 minus 0 over R3. That's what you see on the third and final input term there. And for the feedback resistor RF, the current that goes through that is IF is the same. It's defined the same as it was in the inverting amplifier. That's going to be DO over RF. Then we put the other side equation because we want to solve for DO, and so of course it becomes negative now. So now we have all our input voltages and our output voltage in the same equation, so now we can solve for VO. So let's do that. And so here is what the general equation of the summing amplifier looks like. This is going to be our answer, but we're going to do one little simplification after this. But looking at this equation, what does it tell us about how the summing amplifier works? Well, see that we adjust how important each one of our inputs is to the final output voltage. And how can we do that? Well, you see that there's a constant RF term in all the applied to each of the input voltages, but each input voltage has its own input resistance. Now, those are R1, R2, and R3, so we can individually adjust the importance of each input to the final output voltage, VO. So if we make R1 really big, then we reduce the importance of V1 because the denominator of this term right here gets bigger, so this whole term gets smaller. And we do the inverse, so we make R1 really small. Then we make the term, the V1 term here bigger, so we can adjust how much impact each input has on the final output. Now, what if R1, R2, and R3 are all the same, which we might want to do in some cases? So in that case, if all input resistors are equal, then the output voltage VO is just going to be negative RF over RI, and RI is just a general term for those input resistors, which are now all the same. And then that multiplied by the arithmetic sum of all the input voltages. And we'll note that we'll go all the way up to the end, because we can have as many inputs as we want. We just have to add them up. I just showed 3 here because I thought it illustrated the point. And so yeah, that is our final equation, as long as you